Hi everyone, thank you for letting me speak today. So this is Ghislain Blanchard, I am Maxime Bouyges. We are both working at ONERA, the French aerospace lab, and we are very exciting to be here today to talk to you about solving PDEs with our package Bcube. So today we'll see a bit about the motivations and the architecture of the package. We'll show you some examples. We'll share some ongoing work about HPC developments, and we conclude with some insights. So what is Bcube? Bcube is an open source Julia package designed to solve PDEs on unstructured mesh. It started as a side project around 5 years ago, initially to learn Julia, actually. And the key features are finite element and discontinuous Galerkin discretizations. It provides a high-level and easy API, like you can see here on the screen. And we handle 1D, 2D, and 3D unstructured mesh with high-order geometrical elements, including mixed mesh and also surfacic mesh. So for instance, if you want to solve something around a sphere or an airfoil or whatever. So what are the objectives of the package? What do we want Bcube to do is to manage meshes, to manage finite element variables, including, so it's mainly DOF numbering, to know who is a neighbor of who, how to interpolate a function in an element, etc. To handle system of equations when you have several of them. To manage the assembly of the discrete weak forms, and since I forgot on the previous slide to mention that the package is heavily inspired by other Julia packages, especially GridApp, but also Ferry, Trixie, and so on. We won't go into too much detail about these assemblies. It's very common to the finite element framework, like the loop over the elements and so on. We will more be focused on other aspects. Bcube also provides an I/O interface as well as implementations. We will see that just after. And we provide a high-level API without performance loss. So it's really the idea of the package, easy prototyping, but also performance.
Okay, so to reach all these objectives, we have decided to build an ecosystem around Bcube with several packages that are all available online on GitHub. So on the figure here, you can see all of them. So there are a few packages to read meshes. There are also a few packages to write results. And here you can see the main package, which is Bcube. So this package provides, as Maxime said, all the functionalities to have the spatial discretization of your PDEs. And you can, if you want, couple this package with external packages like differential equation to solve, for example, time-dependent problems. Regarding the high-performance computing, we have started to write two packages, Bcube Accelerated and Bcube MPI. So we will discuss those packages a little bit later during the talk. And last but not least, we have also a package called Bcube Tutorials. So this package gathers commented tutorials as well as more advanced examples to show the capabilities of the package. So now if we take a closer look to the Bcube's architectures, there were, from our perspective, two key ingredients that drove the development of the package. The first one is the use of static arrays for all the low-level and intensive algebra parts in the low-level function. So actually, this choice was pivotal for our design because it affected all the design of the algorithm to ensure that we can know the size of the static arrays at compile time. The second ingredient is a high-level API of Bcube, which is built on the lazy evaluation framework that aims to separate the declaration of the weak expression given by the user from the computational phases, the computational steps that are done inside Bcube. So to give you an overview of this mechanism, you can consider, for example, a finite element function, U, So basically, this finite element function will represent a solution, a polynomial solution defined in the entire mesh. And what is important here is that this finite element function is a subtype of an abstract lazy. It means that if we apply a function g on this finite element function, what you get, it's a lazy operator that contains all the operation tree. And if you want to get the value of g of u at a specific point, so basically it's what we do inside Bcube, we have to materialize this lazy operator twice, first on an element of the mesh and then on the point inside the element to get the value. So this materialization process is actually a tree traversal. So to avoid a performance penalty, we have also introduced a lazy composition operator. So you can define g of u in this way. And with this lazy composition, what we get, it's a new tree, which is much more smaller. And in this tree, actually, the g function can be seen as a black box. So we can deal with very complex operation as a lazy in the lazy framework.
Okay, so let's move on to some examples. So I'm really sorry. At first, we prepared many examples and our speech was like 2 hours long. So we had to remove a lot of them, but we have some backup slides if you are interested in. So I will just mention that all of them are real world applications, I would say. I mean, some equations that we had to solve for our work. So you have fluid dynamics, solid mechanics, you have linear problem, non-linear problems, mesh adaptation, and so on. And I will start by the classic, I would say, mandatory steady heat equation using finite elements. So on the left, you have the Bcube code. You will see that for those who know GridApp, it's very similar to the GridApp syntax. So in the finite element framework, if you don't know, you have to formulate your problem with a weak form. So that's the second bullet, I would say, with a bilinear form on the left, a linear form on the right. And what we want from Bcube is to give us the A matrix here on the bottom and the B vector to solve the problem. So on the left, we have some basic mesh generators in Bcube for fast prototyping. You can then define your function space and finite element space, selecting different polynomials. It's also here that you define Dirichlet condition, depending on time if you want. It's not the case here, but you can input time-dependent Dirichlet conditions. Then you declare some cell domain and other domains, we'll see that later, where you want to integrate, as well as quadrature rules. We have several, again, of them, depending on the property that you want. This is a cool part. You declare your bilinear and linear forms, and it's very close to what you write down on the paper, so that's really cool for us. Here is the core of Bcube. You assemble, so you form the bilinear form. You assemble the bilinear form and the linear form to obtain a sparse matrix and a vector, and they are standard Julia arrays. We don't wrap them into some kind of objects. It's something that we really want to give these natural elements to the user, and he can do whatever he wants after that. You can manipulate these arrays to enforce Dirichlet, and in the end, we don't handle the linear system. It's up to you to invert your problem here using linear algebra, but you can use whatever you want. It's Julia objects, right? And if you like, and usually you need it, you can write down the solution here with the VTK file format. And as Ghislain shown, you can apply any operation on this FE function. So here we can output the gradient, but any mathematical operation can be also performed.
So now let's move on another example with the discontinuous Galerkin method. So for that, we can consider, for example, a simple linear transport equation. And here you have the weak form. So with the discontinuous Galerkin method, what is new is that we have to deal with phase contribution because the solution is discontinuous across cells. So to define these weak forms, we have to deal with some jump of the solution and also to be able to define the normal of the faces to write down the weak form. So this system can be represented as a semi-discrete problem like this. So the goal now is to see how we can compute the right-hand side with Bcube. Okay, sorry. Okay, so the first step is to read some meshes. So one mesh. So here we choose to show you how to read a mesh from a gmsh file. So it's very simple. Then we define the function space. So the difference compared to the previous example that we use the discontinuous keyword here to make Bcube duplicate all the degree of freedom at cell interface because the solution must be discontinuous. Then we can define the new domain that are related to the new terms in the discontinuous Galerkin method. So here we can see, for example, the interior phase domain and two boundary phase domain. And we can also define the measures and the normals that are associated to the phase domain. So all these structures actually are lazy operators, so there is no computation at all at these steps. So now we can move on the loop for the time integration, and you can see that we need to define the right-hand side function with the weak form. So if we move on to the right-hand side function, you can see here that with Bcube formally, you can actually define the right-hand side function in a way that is compatible with differential equation. And what is important here for today is to see that we can deal with the discontinuous solution thanks to new lazy operators called side minus, side plus that allow us to select which side of the face we want, from which side of the face we want to interpolate the solution to define the numerical flux. Here, the numerical flux is just a classical Julia function composed with the side values. So once we have defined this weak form, everything is lazy. So now we want to evaluate the weak form and integrate it over the mesh. So we call assemble linear. And what is interesting here is that this function, we don't have any allocation this function thanks to the design of the architecture of Bcube. So, and finally, you can write the result to get some nice animation. So now we will move on the next part, which is what we are currently doing for high-performance computing. So as I said, we started to develop two packages. So the first one is Bcube accelerated and is more focused on shared memory parallelism, especially for GPUs. So our strategy here was to extend Bcube on GPU by using all the available tools from the Julia community. So the first step was to use adapt.jl, so this package, to make all internal Bcube structures GPU compatible. And the second step was to rewrite some assembling kernels for GPU compatibility thanks to kernel abstraction and also accelerated kernels and atomics packages. So for this last part, actually, the work was quite easier because all low-level Bcube functions were already allocation-free and type-stable. So it means that, for example, for this kernel, you can see that each line actually is just a simple call to already existing function in Bcube. So we can reuse all the previous code, the serial code. As regard the user API, what I can say is that we introduce a new keyword to select the backend, so it's just a minor change. And we also have other change due to the fact that for now we are not able to build directly the mesh on the GPU. We need to read it on the CPU and then move it to the GPU. It's the same for the trial finite element space, but we hope that for the trial finite element space we will be able to do it in the next few weeks. So this package was started just the last summer, so just two months ago, but we were able to try some performance benchmark. So here we have some preliminary results. So the first target for us was the GPU. So here you can see the speed up that we get compared with respect to the serial version of Bcube on the one CPU core. So the speed up is quite nice for us. And if we thanks to kernel abstraction, we were also able to try what we can get from the CPUs. So here you have a strong scaling on this CPU, and what we can see that for now the scaling, the speed up is not linear, so we don't have a perfect result, but at least we are able to switch between different devices, and that is very cool. And the numerical results is correct, so that's very cool also. And we hope that thanks to the dynamics around the Julia ecosystem for the GPU, we hope that we will be able to improve this first benchmark.
Okay, now regarding distributed memory, we developed a Bcube MPI package because we were interested in the performance of Julia code with MPI, and there is not so much unstructured mesh solvers using MPI in the ecosystem. Our main concern was to make something compatible with differential equations. It's also not something that we found in the ecosystem yet. The strategy is quite classical. It's based on domain partitioning. So you divide your mesh and you give one portion of the mesh to each CPU, and they exchange information using a layer of ghost cells. And for this exchange, you basically have to have an MPI-aware abstract array, like partition array. But in our experience, we failed to use a partition array combined with differential equations. So we developed a new package here, at least to get to the point. And you also need a parallel linear solver if you want to do something in parallel regarding ODEs. So we wrapped the PDE library, although there are other wrappers in the ecosystem, existing wrappers. For the in-out, we still read Gmesh files using the GLL, and we write parallel VTK files, so since it's easily supported by write VTK. So everything is working, like for the shared memory example, so it's very cool. But for now, it's more a proof of concept. We introduced a package that we not necessarily want to keep. We'd like to rely more on the Julia ecosystem and less about package that we redevelop at each time. So here is the same example as before, the linear transport equation, but combining Bcube, MPI, differential equations, and PDE. Ready? So we start by reading a partition file. So it's implemented in Bcube MPI. Then you can still assemble bilinear forms. So it returns a sparse matrix. And since you want something that is MPI aware, you wrap it into this container here, a haunted matrix, and it will handle the communication when performing a matrix vector product, for instance. Then what is really cool is that we can reuse the RHS function that presented Ghislain. It's the same code as in the sequential. So the physical part of the equations remains the same, right? And finally, we can define classical differential equation stuff. Not necessarily the last version with differentiation in the interface, but we still have this sparsity pattern, coloring, and so on. It's transparent to parallelism. You then define your ODE problem. And what is really nice here is that we use an implicit Euler time integration, which will involve automatic differentiation, and it works in parallel. and also a linear solver, a parallel linear solver. And here we have our PDE wrapper where you can specify or use any KSP solver you like. I will not detail this slide, is too long, just to mention that we performed simulation on several million of degree of freedoms, again for real world applications on 100 of CPUs. So it works, although the scaling was not perfect. And finally, I'd like to conclude with some feedback about the use of Julia in an industrial research context, which is ours. So I wrote down a few questions that we may face or which we faced discussing with our colleagues about writing Julia codes. And I will not list all of them, but some of them are like, oh, okay, Julia is a young language, will it still be there in 15 years? Or, oh, okay, why aren't you using C++ and or Python like anybody else? Or, okay, you wrote your script in Julia, I wrote my script in C or whatever. Can we interface both scripts? So these are some answers that we try to provide. Again, I won't list all of them. We really like the mechanism of the manifest, which is not specific to Julia, but at least it's put forward, and it's not very common in the Fortran community, I would say, at least in our office. So it's very helpful to convince for reproducibility. We loved the GPU portability. I think it's a really good point for the Julia community, and also, of course, auto-differentiation. And finally, regarding the interface, we found that Julia is already excellent at wrapping other codes, C library, and on the other way, being called by a Python script is quite easy. So it's also an excellent argument for us and to discuss with our colleagues. Thank you for your attention. We leave here some conclusions, and we are happy to discuss here or later on.
If there are any questions, I'm going to run because I have 1 month. That's all. You don't have the issue design defining. Actually, no. Thank you for the very nice talk. I have a bit of a provocative question. Could you comment with the overlap with your... I'm going to repeat the question. Can you repeat the question afterwards?
Yeah, can you comment about the overlap
With GitHub.
with GitHub? Yeah, so we prepared a slide and we decided to delete it. Yeah, there are many answers to these questions. The first one is that we started this project to learn Julia at the beginning, not to build a new package. And writing. After some time, we were like, oh, okay, the project is pretty cool. Then, of course, we looked at GridApp. For a moment, we thought about joining, but as Ghislain explained, and maybe he will correct me, but the internal architecture of GridApp relies heavily on cache mechanisms, and we wanted to provide something that was more easily allocation-free, deep down, like Ghislain showed, and this is what helped us. This is what was crucial to move on to GPU, especially. We basically had almost nothing to modify in Bcube.
But so you're not using, you don't have cache because you use basically static arrays or
Yes. So the goal the main objective with static arrays was to avoid using cache mechanism, because cache mechanism actually is it's quite difficult to deal with this on GPUs and for multi-threading, for example. So we prefer to go on static arrays.